Let me welcome you to this lecture. We have been discussing the chemistry of boron, and so far we have discussed about compounds of boron, different types of compounds of boron. That is, we have discussed about borides, as well as we have discussed about hydrides of boron, that is borans, and we have also discussed about compounds of boron with oxygen. So during this lecture we will discuss about the compounds or chemistry of boron nitrogen uh, compounds, and to begin with, the Bn unit, that is, boron has 3 valence shell electrons, while nitrogen has 5 valence shell electrons. So total there are 8 electrons in the Bn unit. So it is isoelectronic with the Cc unit, which also has 8 valence electrons. Moreover, if you look at the electronegativity of boron, carbon and nitrogen, what we will find is that their electronegativities are quite similar. That is, the electronegativity of carbon is a mean of the electronegativity of boron and nitrogen, and also the size of these 3 elements are also quite similar. So based on this, the chemistry of Bn compounds essentially correlate well with the chemistry of compounds formed by Cc linkages, where there are Cc linkages, and this a good example to begin with is boron nitride. That is, we can write it as Bn. Now this boron nitride, it has 2 different phases are present, or 2 different structural types of boron nitrides are present. One is hexagonal and the other one is cubic. So one can hit the hexagonal phase to obtain the cubic phase, which has zinc blende-like structure. Now the hexagonal phase has a graphite-like structure, while the cubic phase has a zinc blende or zinc sulfide type of structure. So if you look at the hexagonal phase, what we will see is that there are hexagonal boron nitrogen rings which are interconnected like the ones in graphite. In this way, so then there are hexagonal rings, Cc rings in case of graphite, while here we have hexagonal B and B rings are present in case of boron nitride or hexagonal phase of boron nitride. The difference the difference with graphite structure is that in case of graphite, the alternate stakes of these hexagonal rings are not exactly on top of each other, while the carbon atoms are not exactly on top of each other. Carbon atoms of 2 different hexagonal sheets in graphite are not exactly on top of each other, while in case of boron nitride, the boron atom in one hexagonal sheet is actually on top of the nitrogen atom of another hexagonal sheet, which is below it. So that is how it is there. So if you look at the next sheet, what we will see is that the boron atom in each of these, the boron atoms are exact on the next sheet. is actually on top of the nitrogen atom or vice versa that way. So here the atoms lie exactly on top of each other for different sheets, and that is because of the interaction or different type of interaction that are present in case of boron nitride. The inter-sheet distance in case of boron nitride is quite similar to the intersheet or inter layer distance in case of graphite, that is inter layer distance. We will in Bn is 333 picometer, and this is quite similar to the interlayer distance that we observe in case of graphite. One more structural aspect that we can see is that the Bn distance, bond distance, that is within a particular layer, is equal to 145 picometer. And if we look at the sum of the covalent radius of a single bond covalent radius of boron and nitrogen, we will see sum of single bond covalent radius is equal to 158 picometer. So the Bn bond distance or intralayer Bn bond distance, that is Bn bond distance within a given hexagonal sheet is essentially much short than the sum of single bond covalent radius for the boron and nitrogen, which is equal to 158 picometer, while the Bn bond distance is equal to 145 picometer, and this tells us that there is substantial double bond character in the Bn bonds or intralayer Bn bonds in case of the hexagonal boron nitride phase. So this essentially tells us that the hexagonal Bn phase is quite similar to graphite in terms of the structural aspects. But if we look at the chemical behavior of hexagonal boron nitride, what we will find is that this is colorless, unlike graphite, which is colored. Also, it is an insulator, while graphite is a good conductor of electricity, but boron nitride itself is an insulator, and also it is chemically inert. Unlike graphite, which is not chemically inert, which undergoes many reactions because of the sp2 carbon atoms in case of graphite, but boron nitride does not undergo chemical reactions under many harsh reaction conditions even, and it undergoes reaction only with elemental fluorine. So because of these properties of boron nitride, it is used as a lubricant at high temperature or in conditions or where there are high temperature or is involved. So it is used as a lubricant because we know graphite, because of the layer structure, is a lubricant, but because it is not chemically inert as well as it is not an insulator, that is why it cannot be used in many applications, while boron nitride, being chemically inert as well as because it is an insulator, it can be used as a lubricant at under harsh conditions and under high temperature conditions, or in instruments where, or in equipments where there are which are used at under high temperature. So this is a very important application of boron nitride, and we have seen that it has many similarities with graphite, but still it is chemically it is quite different from graphite. So there is another important boron nitrogen compound which has strong similarity with a compound Cc formed by Cc linkage, that is benzene. We know has this sort of structure. So there is a inorganic counterpart of benzene formed by boron nitrogen linkage, and this is known as Borazine. So the structure of Borazine is quite similar to the structure of benzene. So we can draw the structure in this way. So there are dative bonds from nitrogen to hydrogen, boron here, and to each of these atoms a hydrogen atom is attached in this way, the way it is present in case of benzene as well. So this particular compound was initially prepared by Alfred Stock. We have already discussed about Alfred Stock while discussing about the chemistry of hydrides of boron, because Alfred Stock was a pioneer in this particular area, and he did a reaction, that is with B2H6 when he reacted ammonia, so 6 equivalent of ammonia with 3 equivalent of B2H6, so it essentially gave a Lewis acid base adduct initially, that is BH2 in this way. We have discussed about this sort of reaction of diborane with different Lewis bases earlier, and then when you heat this adduct, one isolates, so one obtains B3N3H6, that is Borazine. So this is how Borazine was initially prepared by Alfred Stock, but then now better synthetic procedures for preparation of Borazines have evolved since then, and this is essentially one can prepare Borazines in better yields by reaction of BCl3 with ammonium chloride. Instead of taking ammonia, one can take the conjugate acid, that is ammonium salt, and this essentially gives us Cl3, B3, N3, H3. So one can reduce this by using, or one can replace the chlorines which are attached to the boron here. The structure of this particular compound or intermediate is so hydrogen atoms are attached to the nitrogen, while chlorine atoms are attached to the boron centers here. So one can replace the chlorines by using a hydride donor, that is sodium borohydride one can use, so that one obtains Borazine So in place of the chlorines, we substitute the chlorines with hydrogen atoms in this fashion. So that is a better method, or this particular method for synthesis of Borazine gives better yield. One can also start with NaBH4 itself. So the reaction of ammonium chloride with NaBH4 also gives B3 N3 H6, and NaCl is a byproduct in this particular reaction. So this is an alternate procedure for preparation of Borazines. Then we can also prepare substituted Borazines, or we can prepare Borazines of our, with different substitution on the boron and as well as on the nitrogen atom by starting with the right precursor. That is, we can, instead of using ammonium chloride, we can take alkyl or aryl quaternary ammonium salts like this, RNH3Cl. So this is called quaternary ammonium salt. R can be an alkyl or aryl group here, and then do reaction with BCl3. So then we will get Cl3, B3, N3, R3. So the R groups here are attached to the nitrogen centers here, and then when we do reduction with NaBH4, we will get this sort of substituted Borazine. So we can start with the right quaternary ammonium salt to obtain the substituted Borazines in this way. So we can also have the, sorry, this is hydrogen. We can also have the substitution, substitution at the boron center, and for that purpose, what we can do is that once we have this particular intermediate, we can do reaction with lithium alkyl or lithium arides, which are very useful organometallic reagents. So we can use Li R-, and then we can replace these Cls with R- here, so we can have this sort of product. So this is R attached to nitrogen, and here we will have the R- substitution of the Cls with R- can be achieved by using lithium Li R- here as the reagent. So this is how different substituted Borazines can also be prepared, and because of the uh, resemblance or similarity of many physical properties of Borazine with benzene, as well as the structure of Borazine is quite similar to the structure of benzene, it is termed as inorganic benzene. In fact, some of the physical properties of Borazine are strikingly similar to the many physical properties of benzene. One good example is that if you take the ratio of melting point of substituted benzene with the melting point or boiling point of substituted Borazines. So what we take is here boiling point of substituted benzene with, and take the ratio with boiling point of substituted Borazine. So if we find out the ratio of the boiling point of benzene with the boiling point of substituted Borazine, and if we use similar substitution for benzene and Borazine, and we find out the ratio, and what we will find out that this ratio is essentially constant for different substitutions. So as we change the substitution for benzene as well as for Borazine and take the ratio of the boiling point of these compounds, we will get a constant value for each of these substitution, and this essentially tells that the change in the boiling point upon changing the substitution essentially is similar for both benzene as well as for Borazine, and this sort of, and because of this similarity in the physical properties of benzene and Borazine, this was initially termed as Borazine was initially termed as inorganic benzene. But then the chemical behavior of benzene and Borazine are quite different. In case of benzene, what we see is that the carbon atoms in benzene are sp2 hybridized, and there is formation of pi bond between two neighboring carbon atoms, and this pi cloud essentially is delocalized all over the ring in case of benzene, which essentially brings aromaticity to the benzene ring. But in case of Borazine, the picture is slightly different here. Again, as in case of benzene, all these ring atoms, that is both boron and nitrogen in case of borazine, are all sp2 hybridized, and on each of these ring atoms there an unhybridized p orbital which is perpendicular to the plane of this ring is present, as in case of benzene. But here the unhybridized p orbital on boron center is empty, while the unhybridized p orbital on nitrogen atom contains one lone pair of electron. That is, you can draw one unit here in this way. So the unhybridized p orbital on nitrogen atom contains a lone pair of electron, while the unhybridized p orbital on boron center is essentially vacant. While in case of benzene, what we see is that there are unhybridized p orbitals on all of these carbon atoms in this way, and each of these unhybridized p orbitals contain one electron in this way, and that is how it forms a double bond with the neighboring carbon atom, and these double bonds are essentially all delocalized across all these atoms within the ring. But in case of Borazine, the p orbital, unhybridized p orbital on boron is empty, while the unhybridized p orbital on nitrogen atom carries a lone pair of electron, and now double bond has to form because of donation of this electron pair to boron center, and because of this reason, actually, the ability of nitrogen atom to donate electrons, or the amount of electrons that is donated from the nitrogen atom to the boron center is less, and that is why this double bond is essentially more, this lone pair of electrons are more localized on the nitrogen atom essentially than on the boron center here, and the nitrogen atoms are essentially, in case of Borazine, have basic character, that is, they are Lewis basic in nature, while the boron centers are Lewis acidic in nature. They are electron deficient, while the nitrogen atoms are electron rich, and this creates a dipole moment, or unlike benzene, the BN linkages in case of Borazine, they have dipole moment, and because of this reason, the chemical behavior of benzene and Borazine are entirely different. While benzene does not undergo addition reactions with, but Borazine do undergo addition reactions. So what we will see is that if we do reaction with, say for example, HCl, so there will be no reaction with benzene. But if we do reaction of Borazine with HCl, addition reaction is going to take place. That is, we will obtain a product where the HCl will undergo essentially the Cl groups, because boron centers are electron deficient, so Cl negative will come and attack on the boron centers in this way, while the nitrogen atoms are Lewis basic, so H plus will come and attack on the nitrogen centers in this way, and we will obtain this sort of a addition product when we do reaction with HCl. So that is how we see that the chemically benzene and Borazine are quite different because of this difference in electron density on boron and nitrogen atom, while the electron density on these carbon atom are equal in case of benzene. So under in a reaction that we where this difference is highlighted, that is, we can do reaction with Br2. In case of benzene, it can undergo electrophilic substitution reaction in presence of a catalyst, and what we get is our brominated product in this way. So in presence of FeBr3, we will get this sort of product, brominated product, because of electrophilic substitution reaction. But in case of Borazine, what is going to happen is when we do reaction with Br2, addition reaction is going to take place, and what we will have as a product, this sort of product will be isolated upon reaction of Borazine with Br2, because here instead of electrophilic substitution reaction, addition reaction is going to take place. So that is how we have seen that chemically Borazine and benzene are entirely different, or the chemical behavior of Borazine and benzene are quite different, while the physical properties of Borazine and benzene have many similarities, and that is why, though it is termed as inorganic benzene, or Borazine is termed as inorganic benzene, it is a misnomer essentially. So this brings us to the end of this lecture. What we have learned during this lecture, or what we have discussed during this lecture, is about compounds containing B-N linkage. What we have seen is that the B-N linkage is isoelectronic with the C-C linkage, both containing 8 electrons, as well as what we have seen is that the size as well as the electronegativity of boron, nitrogen and carbon are quite similar, and that is why many of the compounds of containing B-N linkage have a similarity with the compounds formed by C-C linkage. And two different compounds we have discussed here. One is boron nitride. We have seen that boron nitride, the hexagonal phase, has a lot of structural similarity with graphite, which has a layered structure, while boron nitride also has layered structure. Only difference here is that in case of boron nitride, the boron atoms lie on top of the nitrogen atom, or boron atoms of one particular layer lies on top of the nitrogen atom of the neighboring layer, while in case of graphite, these are the carbon atoms of two different layers are not exactly stacked one over the other. And we have also seen that the interlayer distance in case of boron nitride is quite similar to the interlayer distance that we observe in case of graphite. But chemically, boron nitride is different from graphite. That is, it is insulator, as well as it is colorless, and it is thermally stable, as well as it is chemically inert, and that is why boron nitride has found application as a lubricant in case of high temperature applications, as well as another compound of containing boron nitrogen linkage that we have discussed is Borazine, whose structure is quite similar to benzene, as well as many of these physical properties of Borazine are similar to benzene, while there is difference in the chemical behavior of benzene and Borazine because of the difference in electron density between the nitrogen and boron center in case of Borazine, while in case of benzene, all the carbon atoms have equal electron density, and that is why benzene does not undergo addition reaction, while Borazine can undergo addition reaction. And we have seen that while benzene undergoes electrophilic addition reaction with Br2, Borazine undergoes addition reaction with Br2 here. So with this, let me conclude this lecture, and I thank you very much for being with me during this lecture.